Alrighty, so NI Days is coming up in London fairly soon, and I've been doing quite a lot of Simulink lately in my videos, so I thought I'd better do some Labview, try and redress the balance. And the particular Labview I've got in mind is to do with battery cycling, and a lot of this stuff I did when I was a postdoc, and we were working on testing of batteries for hybrid automotive applications, and as part of a suite of CO2 reduction technologies. And I spent a lot of time testing batteries, especially doing lifetime testing and trying to elicit pseudo-random binary sequences to measure system properties or do system identification by looking at the noise the battery had on its terminals and using that to infer its a model of its internals without having to resort to too much electrochemistry. And a lot of the time when we're doing this sort of lifetime testing, you're just charging and discharging and charging and discharging over and over and over and running cycles. And if you have anything to do with batteries, of course you'll know, or cars in general actually, automotive type stuff, you'll know about the NEDC and so forth. The NEDC is actually not great for batteries or hybrid vehicles because it doesn't really give the battery much chance to regen, or the car much chance to regen into the battery. But that's by the by. There are, if you follow the news, a few years ago, a group of people in California sued one of the car manufacturers in a class action because the manufacturer claimed that they could regen a certain amount, and then in practice they found that under real-world driving conditions they couldn't. And that was the big hoo-ha in hybrid vehicles until it turned out that VW were faking their figures with emissions, and then everybody forgot about that and started getting angry with VW. But they aren't the only ones, of course. Some of the Japanese manufacturers got caught as well. So we were essentially, we took a battery that we were provided by the people we were working for, the battery manufacturers or the consortiums of battery manufacturers, and we would do lifetime testing and figure out whether it would work in a certain application. And to do that we spent quite a bit of time building our equipment ourselves. The sort of things that I had were one or two batteries of each type, probably with some special additives or special geometry or whatever. And they were usually modules, so we were looking at 12 volt setups or 48 volt setups, which is strings of 12 or strings of 12s. So we weren't doing a lot of cell testing like you might find Mac or a Digatron setup for, where you've got 32 or 64, 128 channels of 0 to 20 volts with 0 to 5 or 10 amps per channel. We were really thinking about 0 to 60 volts, 500 amps per channel, and we'd have one or two channels going at any one time. And our testing would sort of last about 9 months or so, or 160,000 kilometers was one of the figures we used to look at a lot. And the way you go about that is you'd take your electric vehicle that you're interested in, put the battery in it that you care about, go to Millbrook. If you're not in the UK or you're not to do with automotive, then you might not know what Millbrook is. Millbrook is it's a racetrack, which is somewhat north of London, not that far from Milton Keynes, and it's actually very close to Bedford. And you put your professional driver in the electric vehicle of your choice, and you put some stuff like a D-Space micro auto box or some NI kit in the boot or under the floor or wherever you can find a bit of room, and you get into the CAN bus and you record everything you could get your hands on. Throttle positions, gear, engine revs, whether the heaters are on or not, and battery characteristics of voltage and current. contactor positions. Everything that goes down the CAN bus, you take the log and pick through it afterwards. And you retire to your laboratory with your battery and your bespoke battery tester and this data. And of course that's the reason you do that, is to save money. You don't want to put a professional driver in a car and have them going around a track until the battery's knackered. It costs you an arm and a leg. So we would take this data and run 6 to 9 months worth of cycles on this battery as if it was going around the track, and then we'd have a look at its characteristics and see how much it had aged and if it was still within the limits of what was permitted. And the usual limit at that time was it was okay if the total capacity that you had at any time, total full capacity at any time, was at least 80% of the capacity when the battery was new. And after that it was deemed to be failed effectively, even though it still worked fine, just not with the same capacity. And you'd put it into some second life application like a storage setup, or you could probably reuse it as a GSM base station UPS or something like that. A lot of lead batteries are found in the mobile phone network. Righty, so I wrote quite a bit of Labview for battery testing, and the sort of stuff I was writing was informed by the kind of test that we wanted to do. So I thought I'd talk a little bit about this now, because it gives you some idea about a non-trivial FPGA example. It is small enough to be very nearly trivial, but it does have some stuff in it, and it does do useful things. Whereas a lot of the examples are trivial to the point of being academic, in the sense that they don't actually do anything useful, they just demonstrate certain things. So hopefully this will give you a bit of idea of an application that was actually live. But I need to talk a bit about the other parts of the system first. So we've got a user interface, which is what you actually log in through, and we've got a real-time software which takes control of the cycling and that sort of thing. So have a look at the UI main. This is probably familiar if you use NI. It's quite a common setup, especially if you've been looking at the Compact Rio Users Guide. So we've got some paths where we can set up where the files come and go to, and then we've got a test schema. So each line of the table is a test in a sequence of, or is one step in a sequence of tests, and I've got a few outlined here, which is just the defaults that I've got lined up. So we're doing some sort of microcycle, which is what MUC stands for, and we are charging, resting, discharging, resting, that sort of thing. So we're putting pulses in, effectively, and the pulses are lasting 30 seconds, and the resting is, well, that rest is quite short. Apparently I was in a rush. 30-second rests, and 2 minutes of discharge, and that sort of thing. It's just an example, and this end is just a word that sets the contactors in our system to off. So we have some control settings, perhaps a profile, but there's no profile here because they're just pulses. And we have the usual things that you have in battery testers, like if you're charging, you have a cut-off voltage, discharging, pardon me, a cut-off voltage that signals the battery is flat. And if you're charging, you have a cut-off current which signals the battery is full, and you set the voltage you want to charge up to, and all that sort of thing. And maybe some time limits, amount of charge you intend to integrate, the control law that you intend to use. So if you want to control on voltage, it's a constant voltage. You can be charging or discharging, most commonly it's charging. Current, we just set the current we want to elicit, that sort of thing. And we can set some limits, and we can set up some control parameters that give us the PI values for the voltage and power control loops. And there's an isothermal glycol, propylene glycol, not ethyl glycol, bath involved with this as well, that allows us to have a look at the total energy which is going on. Because we hold the temperature constant, we know how much work the thermal loop has to do to keep the battery at that temperature, so we can have a good look at the battery's losses, which is quite useful. And there's more parameters, endless parameters. And these are all read from an XML file and I may look at the way I parsed the file, because you can actually write, for example here I've got -%0. Minus just means that we're charging the battery. I know that's different to pretty much how everybody else on Earth works, but as I said, when I started all this quite a long time ago, 9 years ago nearly, there weren't very many of us working on it, and I was the only person who was actually doing any practical work. A lot of the other people involved were doing business development or were involved with what we were doing through the university. And I never bothered to check, which is a pretty bad oversight actually, what the rest of the world thought charging and discharging was. So in everything I did thereafter, charging was negative, which is not the way everyone else does it. Since then I've taken to putting minus signs into old code in order to make it right with the rest of the world. But minus means charging, and then %0 means whatever we extracted in the 0th step, and this is the 0th step here. So there's a grammar that looks at and parses. You can do that in other cells as well. Looks at and parses what happens in this table, so you don't have to know everything in advance. It's I suppose it's a bit like dynamic memory allocation in C. Usually you can't do it, but if you bother to write the code, you can. And in this case, if I want to add back what I extracted before to keep the state of charge the same across a number of process steps or sequence steps, you can do that sort of thing. Anyway, this is what the user sees. A bit of debugging for when it all goes wrong, and then we can have a look at the temperature and the battery parameters, the voltage, power and current, that sort of thing. And we can have a look at how the sequence terminated, so what was the cause and whether we hit our expected charges and that sort of thing. So this gives you a bit of online, not debugging, but just checking that everything is going according to your ideas. If your testing is lasting 9 months and you're doing, say, 19 cycles a day with a 5-hour rest, for example, you don't want to have to wait a week to find out that all your data is wrong because of some minus sign that's in the wrong place, or haven't quite typed the right numbers in, or missed a decimal point, that sort of thing. So if you can see in the table how each step is ending and what its causes, and check if that's as you expect. And we can have a look at what the system's up to. So this is our CPU resource usage, and our total. At largest, what's it total? In this case, this is meant to run on a 963 sb-RIO 9637, so it doesn't give you access easily to the largest physical memory block that's free, whereas on the 9636, which was a VxWorks platform, you did get the largest free memory block was easily available, so I changed it to total free memory, but it's a minor thing. The point is, if your memory is constantly going down over the course of a number of weeks, it's time to panic, because it means one day it's going to crash. Right, so that's what the user gets to look at. The real time, we will get to the FPGA, it's just needs a little bit of stuff to couch it in what's going on. We've got messages that we pass back and forth between the UI and the real time, and usually I label up my messages in a certain way so I know who sent them, especially if you've got systems with more than one target chatting to a computer, so you want to run several things in several different places, like as in something in Birmingham, something in Sheffield, something in Bulgaria. It's nice to know who's sending messages where and what's caused them. And if you can look at the name of the message and see that, it helps. This is boilerplate Labview code which uses the network streams to send the messages back and forth. This is the message handler. Watchdog, which is the usual watchdog that you get in compact RIO type templates, where the FPGA will look out for a ping from the microprocessor. If it doesn't get it, it'll reset the microprocessor and drop itself into a safe state. You could have it, when the microprocessor comes back up, carry on where it left off, but I usually have it wait in order that I know it won't go straight to error again, and I can investigate that first error fully without having to wonder how the error stacked up and what went wrong. So it's better to wait and nail down your errors one at a time. Then we get the data for the CPU and the memory blocks and all the rest of it. Save the actual research data. That is passed to a NAT, which is on the same network as this. It saves it locally on the sb-RIO, and then when it hits a certain file size, it FTPs it to a NAT in the background. And then we've got the control loop. Sorry, NAT is network attached storage. NAS, yeah, network attached storage, apparently. This is the control loop that the microprocessor runs, not the FPGA. So we're either running or we're safe state, and if we're safe state, we're not doing anything. So running by default, therefore, must be the dangerous state. It's not that dangerous. And then we have a case structure which says, are we running a sequence or not? And if we are running a sequence, it means that in this test control, we are making our way through the lines of this table, so the sequence is running. And if it is, we might be discharging, we might be resting, might be charging, or we might be running a profile, which is it could be a voltage profile or a current profile, even a power profile. The control method and the fact that we're in a particular mode of operation they're not linked together. Of course, if you're resting, the contactors are open, you can have a hard time getting anything to happen besides watching the voltages. That's pretty much what's going on. So if we have a quick look at maybe the discharge, what's going on here is we're just passing data out of our automatic control system shifter, which is shifting the data for the current sequence step in the table. So that's the sequence step. That's all our config stuff for the whole lot. All our test is here in data form. I'm pushing it into our FPGA and reading back our current and voltage and so forth, and our integrated charge as well. Integrated charge setup to be calculated on the FPGA is the only surefire way I've found of not accumulating the loss or gaining of a coulomb now and then over the course of a number of months. I tried to do it before on the real time, and then I tried to do it when I was post-processing, and I didn't like any of it. So it's on the FPGA, which is a bit of a shame because you have to do some divisions and it takes up quite a lot of space on the FPGA's resources, but it's by far the best way that I've found. So that's how we get from what the user enters in files and configs into the data that actually comes and goes from the FPGA. So the meat of this then, if I can get back to it, nothing like a few windows to make you happy, is there? This is the control loop on the FPGA. We're taking the three reads, so we're not reading a lot of data really, it's only 3 channels and we don't have to read it particularly fast. A few kilosamples per second is more than adequate for most of the things we want, and if we want to do some burst recording where we have maybe 50 kilosamples per second to do some sort of 20 kHz Nyquist bandwidth for some noise setup or something like that. Of course, Nyquist and noise are two terms that you shouldn't really interchange because Nyquist only applies to periodic systems. And anyway, let's not get into the debate now. But suppose you're doing EIS and you want to go very high frequencies, you might want to do some burst mode work. That isn't written into this, but you could. There's no reason why you shouldn't, and you could make it an extra mode on your FPGA that sets up a slightly different sampling setup. Anyway, we get the battery current, voltage and so forth, and we have all the stuff that we've pushed from the microprocessor over, including the control strategy. The control strategy is the interesting bit. Just below we've got the controller for the bath, and we've got the watchdog, and that's the watchdog which resets the microprocessor, and this is the standard Labview stuff. So there's 4 modes available to us. The current mode, rest, voltage mode and a power mode. The reason that I don't have words up here is that somewhere in this code there's more than one definition for control strategy, or perhaps it's defined with a different type attached to it, and I need to go back and find out where that is. But as things stand, this code works and has been tested at very great length, and I'm quite reticent to go back and risk introducing errors, even though it's not quite as beautiful as perhaps we'd like it to be. So we look at the current. We need to decide if the current we're asking for is bigger than the power or the voltage that we'd like to have. So suppose I've been charging for a long time and the voltage on the battery is, if we pretend it's a 12 volt SLI battery, because they're still extremely common. I know lithium is very popular, but just for the sake of argument, let's suppose. If you want, it can be a 14 volt lithium or something like that, that's fine. 12 volt lead battery, and we've been charging for a long time, and we have, say, I don't know, 50 amps charging. We've been doing it for 10 minutes maybe. If it's a 50 ampere hour battery, then chances are the voltage is going to be rising quite a bit now, unless it was empty to start with, of course. Maybe the voltage hits its limit and we need to dial back the power somehow. This is quite common in charging, where you have a constant current for a long time and then you go into constant voltage mode. If you're not going to make that switch in your code, you might want to be able to move seamlessly from one to the other. It's pretty common to want to do that. So we'll see if our power limits or our voltage limits have been exceeded, and if they have, we will cut in this controller. And the controller is just a PI controller. The key thing here is that the controller is always watching. Even when the controller does not have the capacity to act on the output, it still takes the inputs and it still makes a control decision. We can reset it when we want, if we need to, so when we change mode or change sequence step. But if you just cut the controller in cold turkey at the moment where you need to go from current mode to voltage mode, the controller's going to have a transient, and you won't get data that you'd like to see. The controller has to be watching effectively, from not so it can see it coming, because it doesn't see the future, that's not how it works, but you know what I mean. To actually look at the controller itself, nothing major here, it's just a regular PI controller. We're not really trying to do anything difficult in control terms. Batteries have nice long time constants, usually. So we have some possibility of manual control if we want to take over. We're looking at the battery voltage and the demand that we desire, which is a current in this sense. And then we have some control parameters that tell us how much integral gain, how much proportional gain we need on our error signal, which is the subtraction of these two. And we have some limits on the maximum current that's allowed to be output. Output is current because the power electronics that I designed for all this was a linear transconductance amplifier. So you have a small voltage on some analog input pin, and that acts to control a very large current which is flowing in or out of the battery. So our embedded system has to present that small voltage as if it is that current. So when we're thinking about our outputs, it's a current demand. Even though it is a voltage, it represents a certain current, and the representation is the gain of the power electronic system. So that's our setup for the current mode. The rest is nothing much happening there. Even though the contactor is off, we can still measure the voltage on the battery terminals. We have a four wire sense arrangement usually. In voltage mode, we have a PI controller which acts to provide the current demand which is needed to maintain the battery voltage at the set point. And we also need to check that the battery voltage that we're actually demanding is within the limits that the user has set up. So if we had a 12 volt battery and we accidentally asked for 24 volts, you wouldn't end up with a lab full of the smell of vaporized electrolyte in the morning if you left it going all night. There's no current limit here though. So if your battery is only 30% SOC and you ask it to be raised to 14.8 volts, the current will be whatever you can drive in. And that might, of course, kill your power electronics or blow a fuse, but mostly the semiconductor devices will save the fuse, which is a shame because the fuse is pretty cheap, but unlike the power FETs. If we wanted to, you could put the current limit here, and that would be fine. But when you process the data, you've got to remember that it might not be that the battery can't take the current. It might be that your power electronics isn't allowing it. So usually, since it's me doing the test and I trust myself not to make a mistake in this way, I would prefer to have the unmolested data. But if you were running it en masse, or you had somebody else doing it who you weren't confident would be able to make the right choice, you would obviously put it in here and make sure that you don't have any troubles. Last one is the power. There it is. With the power, it's a bit more involved. So you'd have, suppose you're asking to charge at 5 kilowatts, and you can do it because the current and the voltage is fine. The current is not over the limit and the voltage is not over the limit. Then the voltage limit is reached. Now you can't have your 5 kilowatts anymore because you can only do that by exceeding a voltage limit. So you need to reduce the current that's going into the battery to maintain the voltage limit that you've hit. So we end up using this voltage limit path, where we have a voltage PI controller just the same as the voltage loop. And we need to tell the controller that is the voltage limit path that we're interested in. This pathway is always processing the input data, so it's always making a control decision. It's just a question of whether that control decision is allowed to propagate. Similarly, if we're not in the, or if we're in the situation where the power limit's been reached, so that's because the voltage is fine, but the current is such that the VI product is now greater than the power limit. We check the current limit later. Then we move into the power PI controller, and then we have to get that back to current somehow because it's current demand, so we divide through by the voltage. Then we check if we hit the current limit or not. Then we process the data through into the output. So there's a couple of pathways that are involved. Other problem with power is because we do this multiplication of 2 bits of data, you get quite a lot of noise down in the milliwatt level. And since nobody really cares about a milliwatt, or probably they don't, if they do, then there are ways around it. You can deal with your measurement noise in hardware. Then I know this is hardware because it's a virtually hardware, but I mean on your analog side, before you sample, there are methods that you can use, but we don't need to discuss those now. So we just cleave off the bottom milliwatt, and that takes a lot of our measurement noise out. So that's more or less it. All this does is transform from single to fixed point. More or less it. Last thing is, this is how I used to do my integrated charge. It's 40 megahertz is the clock speed. This is, what is this? I don't know what this is. I haven't looked at this code for years. Oh yes, this is, right, I'm with it now. What's that one? Right, the current times the time in the current step, in the present time step. So this is the time between the time step we're in now and the previous time step. So it's the amount of time that's elapsed since we last did the calculation. That's the current that flowed during that time step, and it's presumed to be constant because we only have one sample anyway. Change to fixed point, multiply to get the charge in the time step, divide by the number of ticks per second, integrate, divide by 3600 to get it into ampere hours or ampere seconds. Doing that here is quite costly because we've got two divides. It's costly in terms of silicon area. Actually, this whole business we have here is not particularly demanding of the amount of resources that are on a 9637, sb-RIO 9637. So it's okay to do this. But if we were trying to do a sort of a rack of cells where we had current and voltage and for 60 channels or something, we'd have to look pretty carefully about how this was done, because it would use way too much IC resources. But for this sort of thing, it doesn't really matter that I've been a bit wasteful. Righty, so that's the sort of thing that I did in battery testing. All sorts of other things that were related to it as well. We had some really interesting batteries turn up. I once had a lithium pouch cell turn up from a manufacturer, and it was a set of 6 pouches, and there were just 2 bare wires with tape over one of them, and the battery itself, the case, was FR4, the circuit board material. 5 pieces and 1 little bit on the top, 6 pieces, but the top wasn't whole, and it was all held together with brown parcel tape, and that was the battery. And I don't know how they managed to get anyone to ship it to us. I guess they lied about what was in the package, because it was. If you work with batteries a lot, you get used to them, and you know to cover the end of your wrench in sparky tape and that sort of thing, just in case you have your spanner on the nut of the plus anode, and you touch the case of your equipment or something. There's a big bang. But that battery stood out as the one that frightened me a lot. But actually, it ran for at least 6 months. It wasn't an automotive one; that was for a different application. But yeah, it was good fun. If you've got problems to do with Labview, or you're interested in battery testing, or want to know something about batteries that I can help you with, or make a decision about, or even just point you in the right direction if I can't help you, feel free to drop me an email. I'm available for consulting on a per day basis, and I can come and see you, and we can have a bit of a chat and see what it is you need, if I can help you with it. Alrighty, email me if you have any questions.